Mr. Fernand, I would like to say many thanks to you all for giving me the chance to make a presentation on this beautiful city in Zagreb. So today I would like to show our result using the low energy laser pinning. It can prevent the distortion of the material. Usually laser pinning has a huge laser, has a high energy, so it can distort the material if you apply the laser pinning to the thin material. So we actually this one we actually develop a more hyper microchip laser, and by using this laser, we can construct such a small, compact, portable laser pinning unit. We can carry it freely. For example, actually, we brought it to the Europe 2 years ago, so it is easy to bring. And so we can do this, for example, such a laser pinning to the welded material and confirm the to improve the fatigue strength. So today I would like to do the effect on the laser pinning to the aluminum alloy A5083. However, if usually we apply the laser pinning with high power, for example, it bends like this. However, in our case, the laser energy is very small. For example, 10 millijoule or something, it can prevent distortion. So usually laser pinning use such a laser. This one is a smaller one. However, for example, LSP technology or the metal improvement use a huge laser system. So it cannot bring anywhere. And so we develop a very compact, however, high peak power lasers like this. So and by using this, we construct such a system and apply the thin welded materials. So however, we must be two important things we did. One is to reduce the pulse width, and another one is to reduce the spot size. That's increase the peak power intensity. It determines the plasma pressure. So by reducing the pulse width and the spot size, we can keep the peak power intensity, namely the plasma pressure, to induce permanent strain on the material. So this one is the microchip laser we developed about 7 years ago or something. This one is a laser chip. So this microchip laser integrates all the optical elements. For example, laser medium here and mirrors coated here, and also the Q switch here. So by means of the room temperature bonding technology, if you're interested in the room temperature bonding technology, you can see the detail in such a literature. So advantage of this microchip laser is the compact and robust, and the short pulse duration due to short cavity length, this one, and resulting high peak power and low thermal effect. So this is the mock-up of the laser pair high low energy laser pinning system. We use the microchip laser here, about the 10 millijoule and 100 Hz deposition rate. So this one is a demonstration of the laser pinning. So this is a pump. This is a small robotic pump. So this one is another type of the laser pinning system. We use another microchip laser here, this one, and the laser pulse emitted from this laser hit the material here via the two mirrors, and here is a small lens. It converts the laser pulse on the material. Here is a linear stage scanned. In this case, the material sample is scanned by linear stages. So this one is a video of the pinning. So you can see the plasma here. So this one is a 2 millimeter thick aluminum alloy A5083. So this one is the chemical composition and the mechanical properties of the material we use in our study. So these are the external view of the our sample. This one is base metal, and this one is the welded sample. So dimension is here. So let's go to the residual stress of the base metal sample. So at first we use the XRD. This one is XRD equipment we used in the Osaka University from the Parastech industry. And method is cosine alpha, and these are the parameters used to measure the residual stress of the aluminum alloy. 311 plane is used, and the chrome K alpha we used. This one is the electrolyte polishing device. We measure the residual stress profile by repeating alternately the electrolyte polishing and the surface stress measurement. So this one is the typical result for the AS5083. And we fix the spot diameter about 0.2 millimeter or something. And we change the pulse energy, in this case, 0.6 and 1.0 millijoule. Very small compared to the conventional weather field. And pulse density, however, pulse density is fairly high, 100 to the 1600 in this case. So you can see the 400 pulse is enough to induce a compressible residual stress on the surface by comparing this one in the, it's changed. So around the tensile strength is about 275 to 350 around here. So the 400 pulse is enough to induce compressible residual stress in the surface. So the further, for the further experiment, we use the 400 pulses per square millimeters. So this one is a depth profile. Again, we use in this case 0.6 and 1.0 and 1.7 millijoule, and pulse density is fixed 400, and spot diameter is 0.18. So low energy laser pin induces a sufficient compressible residual stress on the surface, in the surface layer, and which may prevent distortion and enhance fatigue properties. So we confirmed. So residual stress of the welded sample. So this one is the device learnings obtained by the our XRD equipment. So you can see the nice device learnings there. So even if the heat affects the zone. So before laser peening and this one after laser peening. Laser peening can induce some distortion on the crystal. So it enhances the what you say, beautiful device learning to get the beautiful device learning. The error of the regression is very small, about the less than 10 megapascals. So it is very accurate for each measurement. And this is the typical result for the one welded sample of the residual stress measurement. Again, the same parameters. So we measure the 4-point like this, shown by that one. And this we compare the result like this. So by increasing the pulse energy, we can get more higher compression on the surface. However, 1.0 millijoule is enough if you compare to the tensile strength of the material. However, this one is the base metal sample of the residual stress value. So because I think the laser peening, laser welding may decrease the hardness of the material. That's because we cannot induce higher compression compared to the base metal samples. So this one is the surface residual stress on the huts before and after laser peening for the 9 samples here. And 1 to 9 mean the sample number, 1 to 3 or something. And we measure again the 4-point A, B, C, and D here, A, B, C, D. So you can see the 0.6 millijoule is less compressive, induced less compressive, and it has a larger scatter compared to 1 millijoule or 1.7 millijoule. So we selected 1.0 millijoule for the next, for the further experiment. However, fatigue experiment, we did each samples. So this one again the comparison to the result for the base sample, base material sample. Then I move to the fatigue test results. So this one is a fatigue, when the pre-bending fatigue testing machine in the Saitama Institute of Technology. So Professor Masaki, next speaker, will explain the, do the fatigue testing. This is the fatigue test conditions. So this one is a typical preliminary result of the fatigue testing of the welded sample and the base metal and welded sample after laser peeling. So laser peeling is did the pulse energy with 0.6, 1.0, and 1.7 here, like this. And also the white circle in the as well, and black one is the base metal sample. So as usual, welding decrease the fatigue strength like this, but the laser peening partially restore the fatigue strength like this. So recovery is not sufficient, but the optimization of laser peening conditions may further improve fatigue properties, I think. So let me conclude my presentation with this view graph. So as I explained, we confirmed the effect of low energy laser peening with about the energy of 0.6 and 1.0 or 0.6, 1 or 2 magnitude of reduce smaller compared to the conventional laser peening system. However, we got a promising result to get the high compressed cells on the surface, and we prevent the distortion of the material and increasing the fatigue strength. And finally, for the future work, we initiated the simulation experiment to maximize the benefit of the portable laser peening system, which can carry anywhere. And to apply it, we will want to apply it to the existing infrastructure. So this one is the fatigue testing of the simulating experiment of field application. So thank you very much.